Good afternoon, all. So today I will see solution thermodynamics and solve some problems. So I think all of you have gone through the week 7 lecture available on SOM portals. So starting from the fundamentals property relations. As we know, the total Gibbs energy equation for closed systems d ng equal to nv dp minus ns dt. Here n is the total number of moles of the systems. It applies to the single phase fluid in a closed system where no chemical reaction. So for such a system, the composition is naturally constant, and therefore we will get this one. So dg with the differentiate dp at constant temperature and pressure. For differentiate with temperatures at constant pressure and it might. So here the subscript and indicate that the number of moles of all chemical species are held constant. So for open system, so here Ng becomes function of number of moles of chemical species and temperature and pressures. Like Ng is equal to Pt N1 N2. Here Ni is the number of moles of species I. Now take a total differentials of Ng is then the Ng differentiate with dP at a constant temperature and pressure. So dP similarly with differentiate with the dt at a constant pressure and moles. Thus summation from starting a value dng divided by dni at a constant pressure temperature Nj. So here subscript Nj indicate that the all moles numbers except I are held constant. So here the final terms is denoted by the mu I equal to dng dni pt nj. This is called which equal to the mu I. It's called the chemical potential of species I in the mixtures. So this index, this is index of chemical equilibrium. Like pressure, for the pressure is an index for the mechanical equilibrium, and temperature is an index for the thermal equilibrium, right? So here chemical potential is an index of chemical equilibrium. So now first to partial this partial derivative replaced by nv1 minus ns from this session. So you will get this dng equal to nv dp minus ns dt plus summation of mu I dni. So that equation is a fundamental property relation for the single phase fluid systems for variable mass and composition, right? Now take for special case 1 mole of solution ni equal to 1 and n is equal to put xi. I is equal to ni by n. Here n is equal to 1, so xi to so replace ni terms by dxi here. Now the summation of xi is equal to 1, so you will get this term. So you will get v equal to dg by dp at constant temperature and x small fractions. S is equal to minus dg by dt dx. Then consider summation of xi is equal to 1. So from these relations, we can write down for the enthalpy. So we know the H is equal to G plus Ts. Yes, just by these terms, we will get H is equal to G minus T dg divided by dt px. The coming to the partial molar property, the mi with bar equal to dnm divided by dni pt at constant pressure temperature Ng. Here Ng is subscript indicated the except for the species I, the moles of all other species in the solution are held constant. So partial molar property indicates the contribution of a particular component in that of mixtures. So for the pure species, mi with bar equal to the m. So for two means binary mixtures means phase equilibrium between liquid and vapors. So mu I liquid equal to the mu I vapors at a same temperature and pressures. Means mu I alpha. Here alpha is indicate the one phase. I beta also other phase. So chemical potential is equal at the same temperature and pressure, right? Now this is a summability relation. M is equal to summation xi mi. This is a Gibbs-Duhem equations at a constant temperature reduce into summation xi dmi equal to the 0. So in a binary mixture at a constant temperature and pressures, so summation xi dmi equal to 0. So you can write down the xi the dmi with bar plus x2 dm2 with bar. This is also Gibbs-Duhem. So coming to the question number 1. For an ideal gas, the partial molar property is identical with pure species at a mixture temperature and pressure. This statement is valid for. So here is the properties here given. So volume of ideal gas V equal to RT by P, right? Partial molar property Vig Dn Vig Dni P and Ng, right? Put this value here. By P Dni P P Ng, right? By P Dn by P, right? So this for here is a n. So suppose one species. So it this term say come into 1, right? RT by P. So here volume it means almost equal, right? Vig Vi equal to RT by P. So you can derive for the other properties also. But the statement is valid for the only value. Ideal gas of partial molar property is identical with pure species at the temperature and pressure. The question to the partial molar volume of species I in an ideal gas mixture is equal to the molar volume of pure species I at the mixture temperature and pressure. Question number 3. The partial molar enthalpy of species I in an ideal gas mixture is equal to. So in option first, the molar enthalpy of pure species at the mixture temperature and pressure is given, but here is valid only the volume, not for the enthalpy. So option to be given, the molar enthalpy of pure species I at the mixture of temperature and pressure equal to its partial pressure in the mixture. This is right. So Pi equal to Yi RT by VIG. So pressure equal to the partial pressures in the mixtures. Question 4. If Mi with bar, Mi with superscript R, Mi with superscript E are molar, partial molar, residual and excess property respectively. For a pure species I, the mixture property M for a binary non-ideal mixture of component 1 and 2 is given by. Option are given. So as we know, the for the binary mixtures, so M is equal to x1 M I x2 M2. So for ideal mixture, Mi bar equal to Mi. So hence M is equal to xi plus x2 M2. So this is for the ideal gas mixture. This is for the non-ideal. So solution of question 4 is okay. Question 5. The partial molar enthalpy of component in an ideal binary composition. It denoted by J at the temperature and pressures P. The function only. Option here given. So as you know, the internal energy and enthalpy is a function of temperature. And a function of temperature only. Yeah, right. Now question number 6. The need arise in laboratory for a 2000 centimeter cube of antifreeze solution consisting of 30 mole percent methanol in the waters. The watt volume of pure methanol and pure waters at 25 degree must be mixed to form the 2000 centimeter cube of antifreeze. Right. The partial molar of methanol water 30% methanol solution and their pure species molar volume both at 25 degree are given here. So from the summability relations, so V equal to xi V1 bar plus x2 V2 bar. Right. Here x1 is the x1 indicate for methanol and 2 indicate for the waters. So x1 here is 0.3, 0.7. 38 and 6 T2 plus 0.7, 17.765. Right. 4.025 centimeter per mole, right? So because the required total volume of solution is Vt equal to 1000 centimeter cube, right? The total number of moles required is N is equal to Vt by V, 1000 20 83.246, right? So for 30% is methanol, 70% is water. So N1 0.3 83.246 24.974 mole. Similarly for the water, into 58.72. Now the volume of is pure fish is Vt1 Ni, right? Here give V1 V2 given, and we know the we calculated Ni, N1 and A2. Now V1 for methanol 24.974 40.724 equal to 1017 centimeter cube. For water 1053. This is a pure the volume of pure methanol and pure water must be mixed to form 2000 centimeter cube of antifreeze. So question number 7. The volume of aqueous solution of initial at 298 Kelvin was measured for a series of modalities, moles of solute per kg of solvent, and it was found that the volume varies with the molality according to the following expressions. This expression given. So where m is the molality and V is in a meter cube. Calculate the partial molar volume of the component at m is equal to 0.1 mole per kg. Okay. The partial molar volume for initial volume of initial. So V1, one here indicate the initials and two indicate water. dV dNi equal to N2. Here is a m given, so dV by dm into, right? Now this is the equation number 1. Now differentiate these equations with reference to the m, right? So V1 bar will get 0.1662 10 to 4, 0.2655 plus 10 raised to power minus 5.5 0.4 to 10 raised to power minus 6 meter, right? This is equation number 2. Now, so you have to substitute m is equal to 0.1 in equation 2. So you will get v is 0.1748 into 10 raised to power minus 4 meter cube per mole, right? Now substitute m is equal to 0.1 in equation 1. Okay. 1.0047 to 10 raised to power minus 3 meter cube, right? But from the summability relation, v is equal to n1 v1 bar plus n2 v2 bar, right? So here we consider n1 is equal to m1 v1. Now n2, it is a mention the molarities. So 1000 divided by 80 molecular weight of the water, v2, right? Now we know the v value, v1 value, m value. We have to calculate v2 0.05 10 to the power minus 6 per cube per mole, right? So we calculate the partial molar volume of the component. So here partial molar volume of initial is over 0.174 into 10 to the minus 4 meter cube per mole. For water 18.05 into 10 to the minus 6 meter per mole. Question number 8. The partial molar enthalpy in kilojoule per mole of species 1 in a binary mixture is given by H1 bar equal to 2 minus 60 x subscript 2 square plus 100 x1 and x2 square, where x1 and x2 are the mole fraction of species 1 and 2 respectively. The partial molar enthalpy in kilojoule per mole rounded up the first decimal place of species 1 at an infinite solution. So we have to calculate the partial molar enthalpy of species 1 at the infinite dilation. So the partial molar enthalpy of species 1 at infinite solutions when x1 tends to 0, x2 tends to the 1, right? Here is asked for the species 1. So s1 infinity. So put x1 equal to the 0 and x2 is equal to 1. So 2 minus 60, that x1 is 0, this term 58, right, kilojoule per mole. Suppose here ask for calculate the partial molar enthalpy for species 1 and species 2 at infinite. So for species 2 10 to 0 x1 is 1. delta H lead to, right? Result. Question 9. The partial molar enthalpy of mixing in joule per mole for benzene component 1 and cyclogen component 2 at 300 Kelvin and 1 bar given by delta H1 equal to 300, sorry, 3600 x2 square and delta H2 equal to 36 to x1 square, where x1 and x2 are the mole fraction. When 1 mole of benzene is added to the 2 moles of cyclogen, the enthalpy change. We have to calculate the enthalpy. So delta S mix equal to summation of xi delta H1i with bar, right? Here is with the bar, right? So I can write down x1 delta H1 bar, x2 delta H2 bar, right? Now mole fraction xi is equal to ni divided by total moles. Ni equal to n xi, right? So at the time write down equation 1 in this form. So n delta H mix equal to n1 delta plus n2 delta H2, right? Here delta H1 expression given here, so put here n1 to square plus n2, right? Now first we have to calculate the mole fraction for 1 for benzene. So n1 plus n2. Here is a mention that 1 mole of benzene added to the 2 moles of cyclogen. So 1 plus 2 equal to 0.33, right? So x2 is equal to 0. Put this value here. It is 24 joules. Now coming to the partial properties in binary solutions. So as a summability relation, m is equal to x1 m1 with bar plus x2 m2. Now take a differentiate. This will now as we know the Gibbs-Duhem equations. So they express here x1 dmi, x2 dmi. Now for the binary solution, x1 plus x2 is equal to 1. Now the differentiate dx1 dx2. Right. Now, so these terms get cancelled. Now replace uh, dx2 by dx1 minus dx1. So you will get this dm by dx1 equal to m1 with bar minus m2. Right. Now m2 equal to m1 bar minus dm by dx. Now put this m2 value here in this expressions. So you will get m1 bar equal to m plus x2 dm dx1 for species 2 m equal to m minus x1 dm by dx1. Now based on this two equations, we will solve some problems. Question 10. At 30 degrees Celsius and 1 atm, the volumetric data for a liquid mixture of benzene B and cyclogen C are represented by, where Xb is the mole fraction of benzene. Find an expression for a find the expression for the partial molar volume of two components Vb and Vc. Right. As you know, the summability relation M is equal to x1 m1 bar plus x2 bar. Right. Just we derive the two equations. So for m1 bar equal to m plus x2 b m by dx. For m2 m minus x2 dm by dx. So replace m by v1 plus dv by dv. dx. Now put the value here and differentiate with the x1 similar bar for v2. So you will get v1 denoted by sorry vb. So you will get 92.6 and put the value of v here 5928 xb plus 2.64 xb. Yeah, right. And we see 109.4 2.64 xb square. Right. Now you two checks. So you can put the value here. You will get this. for the confirmation. Now question number 11. The enthalpy of binary liquid system species 1 and 2 at a fixed temperature and pressure is represented by the equation. This is the equation. Here H is a joule per mole. Determine the expression for H1 bar and H2 bar as a function of X1, numerical value for the pure species, enthalpy H1 and H2, and numerical value for the partial enthalpy at a infinite solution H1 infinity means superscript infinity with bar and S2 infinity with bar. So here H, this is equation 1. So first replace by X2 by X1 in equation 1. So you will get 600 plus 180 X1 to 20, sorry, minus 20 X1 Q. Here X2 replaced by 1 minus X1. Now differentiate this equation by dx1 180 60 x1 square. Okay. So as we know the two equation derived, so for h1 equal to h plus dx2 deh by dx1, right? For h2 h1 dh dx1. So put the h value here and dh by dx put here. So you will get h1 bar, right, and replace by x2 with 1 minus x1. So x1 equal to 420 minus 60 x1 square plus 40 x1 cube, right? Equation 2. Now similarly for calculate for h2, 600 plus 40 x cube. So we derive for the h1 bar and h2 bar. Now we have to calculate for infinite dilutions, right? So here for the h1, so x1 tends to 0 and x2 tends to the 1, right? So h1 infinity with 1 equal to this gets 0, so 420, right? Joule per mole. हम equation 3 s tend to 0 and x tends to the 1. So s2 with bar equal to 600 plus 40, so 640. A question tell at a constant temperature and pressure, the molar density of binary mixture is given by rho is equal to 1 plus x2, where x2 is the mole fraction of the component 2. The partial molar volume at infinite dilution for component 1, V1 infinity with bar is. So in this questions, the molar volume V equal to, right, so molar density. Now we know V1 bar to V plus x2 dV by dx. So here V is equal to 1 by V. So here rho value given plus x2, right. Now put this value in this equation. So V1 bar 1 by 1 plus x2, right, x2. So d by dx, dx1 by 1 plus x2. So for binary mixture, x1 plus x2 is equal to 1, right. So x2 is equal to 1 minus x1, right. So plus 1, 1 plus, so 2 minus x1, right. So put this here, v1 here is the aspect of the v1, that's why here is the replace 1 2 minus x1 plus x2 d by dx1 1 2 x1, right. Now to evaluation for this terms, so let z is equal to 2 minus x1, differentiate dz is equal to minus dx, right. Now d by dx1 1 divided by 2 minus x1 2 1 by Tz equal to 1 by Z, 1 by, so d by dx1, 1 by 2x1, 1 by Z square by 2 minus x1 square, right? Now coming to the previous equation, p1 bar 2 1 2 minus x1 plus x2 2 minus x1. So for infinite dilution of component 1, x tends to 0 and x2 tends to the 1, right? So va1 infinity with bar equal to 1 by 2 plus 1 by 4, so 3 by 4, 0.75, right? So partial molar value of at infinite dilution for component 1 is a 0.75. Now question number 13. The molar volume V of binary mixture of species 1 and 2 having a mole fraction x1 and x2 respectively is given by V is equal to this expression given. The partial molar volume of species V or species 2 at x2 is equal to 0.3. So V equation given, expression given for V. So now we have to calculate the V2. So V2 bar equal to V minus x1 d by dx1, right? So for the binary mixture x1 plus x2 is equal to 1, so x2 1 minus x1, this is it, right? So replace x2 by x1 in the equation 1, right? So v equal to minus 40 x1 cube minus 10 x1 square 90 x1 180, right? When x2 replace by 1 minus x1 in equation 1. Now take a differentiate with the x1. And now put the value of v with this value here, and with the differentiate, so you will get v2 bar equal to kt x1 cube plus 10 x1 square plus 180, right? v2. Now here is given x2 is equal to 0.3, v2 equal to, so x2 is equal to 0.3, so here x1 0.7, so we will get 2 1 12.3 moles. Right. So here is not even the unit like cube per kilomole. So I cover all the questions. Thank you all. We will meet on next Saturday, next chapters.